Good afternoon, everyone. This is Pouya Banibayat, and today I have a session for you on steel curved bridges and talk about the skew and the curve effect on this type of bridges. This is a follow-up session based on what we had 2 weeks ago, and then Dr. Diana Nevling from the Michael Baker explained about the consideration would need to be considered for the during the construction of this type of bridges. Okay, so before I start the presentation, I should note that the information on this presentation are taken from Steel Design Handbook of Federal Highway Administration (FHWA) and also from the guideline for steel girder bridge analysis of American Associated of State Highway and Transportation official National Steel Bridge Alliance. So I didn't use all the information here, but I kind of like summarize whatever the consideration have to give you better understanding of designing of this type of bridges. Okay, so for today I have 4 parts. First, we talk about the curved and skewed steel girder bridges. We talk about why this type of bridge, like when they are skewed or when they are curved, why the behavior is different from the straight bridges, and then what we have to consider in this case. So talk about the behavior, talking about the torsional stress effect, and I separated them into the I-Girders and box girders. Talking about the torsional deformation effect and load shifting phenomenon. So after that, we talk about the finite element methods of modeling, which are used for modeling steel girder bridges, and talk about the some analysis required for this type of bridge, like construction stage analysis, integral abutment and temperature loading, and moving load analysis, buckling, and extreme loading cases. Extreme loading could be earthquake or flooding, but here we just talk about the earthquake. And finally, the design consideration, talking about like a couple of points like girder arrangement, girder spacing, and constructability. Okay, so behavior of curved and or skewed steel girder bridges. Let's see what's different. What's make these guys different from the straight steel girders. This effect, the behavior of curved or skewed bridges, could be generated in 2 main categories. One is the basic behavior, one is the curvature and skewed effect. So the basic is common with the straight bridges, and you are seeing something like a shear and bending moment effects, and also the vertical deflection and major axis bending rotation. But for the curved and skewed bridges, we are seeing the torsional and warping stresses, but those are pretty important to be calculated, so we don't want any surprises. We definitely need to calculate them or see their effect during the analysis before we come up with the final design. Then the flange lateral bendings, we have the load shifting and warping effect, which I talk about them later on in the following slides, and the twisting deformation. For the torsion, we have 2 effects. One is the torsional stress effects, and another one will be torsional deformation. We'll talk about both here. Due to the offset of the loading when we have the curved bridges, resultant from the chord line drawn between the resultant vertical support reactions, a net torsion reaction is required at the support to satisfy the overall equilibrium of the span. This description can be also extended to describe the development of a overall torque of the bridge cross section. So technically, when we have those curves, we are seeing an additional effects which are going to show you graphically to have better understanding of them. All right. So I put them in 2 categories in the, effect of those torsional stresses. One would be the I-shaped type of girders, another one would be boxes. So for the I-shapes, let's see when we have the axial force, bending moments in both directions, and also the torsion, what gonna be our total normal stress. So the normal stress, as you can see here, has 4 components. What is the effect of the axial forces? So simply you can just divide the force divided by area, so you give us a normal force. On top of that, we have the effect of bending moments, and as you can see, this will be the distribution because it will be about the neutral axis in the x direction or in the y direction. And then we have the other effects for the my, and finally we have the warping normal stresses. Alright, so it's gonna be the same thing for the shear stress. So we talk about the normal, now it is shear. So in the shear, what we have is one, shear forces in both directions, Vx and Vy, and then we have the torsion again. So you can see that in the shear stresses, we see these 2 main components, which are for the Vx and Vy, and then we are seeing the warping torsion as well, adding to those guys. So you can see the direction of them, and then you can guess the how the deformation going to be. So later on we talk about the deformation as well, that these additional stress or additional torsion is causing to the section. So okay, those guys were related to the I shapes. Now when it comes to the boxes, let's see what we got. So we have the exactly the same components for the normal stresses, and as you can see, it has a little bit of different because in the I shapes we had the webs in the middle, so we are not seeing any stresses in the sides. As you can see, for example, the warping effect here is like a more understandable, and then you see it more visually here compared to the I section here, because all parts of the structure is kind of involved in that warping deformations or warping stresses. Alright, the same thing for the shear. When we have the boxes, and then again those shear forces and torsion, you see the main components coming from the shears, and also additional torsions coming from the warping torsion. Alright, so in addition to causing the significant stress in the both I shapes and box girders, torsion also causes significant deformations. So as you can see here, curved girder not only deflect vertically, but also they twist, as you can see in this slide. And they not only experience the major axis bending rotation, but they also warp. So you can see the effect of these like additional rotation, also the additional warping section. So these are pretty significant and important for the design of skewed or the curved bridges during the construction. These are pretty important factors. Okay, so let's talk about the load shifting phenomenon. So earlier we discussed about that and see that in the curved bridges we see such a thing. So let's see what's going on here. What we discussed here, what we said about the torsion and then the stresses, we're talking only about the single girder. But we have to understand that the bridge itself is a system, is not a like individual girders, because we are connecting them with the concrete deck, and they are working together. Therefore, they have effect on each other. So when the number of girders increases, and then we have these curves, what happens is that we have the 2 effects. One of them is the effect of the axial forces, as you can see here, like a primary vertical load system that we got here. So we get almost equal loads there. But we have also the effect of the bending moments because of the shifting the axial force and neutral axis of the entire system compared to the straight bridges, and therefore we are seeing an additional moment applying on the structure. And as you can see, the resultant or the net forces on top of those will be different. So you're technically seeing the larger forces in the interior or the bottom part, which is like inside, and outside we are seeing the smaller forces. All right. So coming back to the modeling part. So the first part was about the consideration and then the effect or behavior of the curved and skewed bridges. Now, an engineer should be able to analyze and understand these effects and see those effects in the analysis. So let's see how we can model those parts, how we can use the software to come up with the result of whatever we discussed theoretically. You need a correct modeling, and you need a good tool to be able to see all those effects. Let's see what available options do we have in the general software for modeling such as I-Girders, curved steel girder bridges. So the first option is a 2D girder analysis, which you just modeling the girders with cross frames, and then it's like a grillage model, and that's just 2D. So you are not seeing any 3D effect. You are not seeing any of those torsional effect. You are not seeing any of buckling and things. So that's pretty basic and simple, and you are losing a lot of the effects that are available on the is available for this type of bridge. The next step, or the a little bit better model, would be a plate with an eccentric beam analysis method, where you have this 2D model, you are just giving eccentricity to the beam, and then a kind of modeling it as 3D. But that's not also pretty. It's not very good to be comprehensive and completely give us the result that we are expecting. So the most accurate way will be modeling a 3D finite element model. We can use a beam element or plate element in 3D and then see all those effects. So we talk about these, and I told you that what options are available in the software, and then what are the methods of the modeling of these. And today I'm not going to show you the modeling. We have another session next week. Please just join us there, and I'm gonna explain you, open the Midas civil software, and show you how you can use the software to do those two type of modeling. All right. Technically, we have three main elements in finite element. We have one-dimensional, which we call it also beam or line element. We have two-dimensional, called plate element, and then we have three-dimensional, which called solid elements. So each of these elements could be used for modeling a curved steel bridges, and each one have their own advantages and their own limitations. For example, let's start modeling with the solid element. Of course, if you model the entire structure with the solid element, you are modeling it very accurately. You are modeling you are seeing the real behavior of the structure, and as I say, it's very accurate. But there is some limitation on that and some disadvantage on that, which is it takes a long time to do the modeling. It takes longer time to perform the analysis, and if you want to do any changes on that, it will be all time consuming. And because of that, that's not very common amongst the civil engineers or bridge engineers, unless you are doing a local analysis. If you want to study a certain part of a structure with more details and become very accurate, that will be a very good option, but not for a global analysis or modeling entire the structure with the solid. So the next element that we could use would be plate elements. So the plate element is actually very helpful and in between the beam element and the solid, and it's giving us a very, very good result and acceptable for the code, and I can say very accurate results. So when we are using a plate element, you can model the webs, the flanges, and the concrete topping, everything, stiffeners, all of them with the plate element. You have to ensure there is a nodal connectivity between those, which means they are working together. And you can do any changes you have. For example, in this model, you see that there is an opening here, so we can simply model that with the plate elements. With the plate element, you can simply see the buckling analysis. You can see the local buckling, and you can see those warping effects, warping stresses. All of them could be seen by plate element. So this model is actually, this element is pretty common amongst the engineers, and sometimes they use plate element to model their curved steel bridges. Another, the simple method is using a beam element. So we talked about the solid and the plate. Now let's talk about the beam. So the beam will be one-dimensional. Now imagine that this is your bridge. Here I have an example of a straight bridge, but just for the demonstration. And what you can do, you can simplify this bridge with a grillage model or idealized model. So by that I mean, we assume that there are longitudinal beams, which are main girders, and then to model the concrete deck, we are using we have to use two things. One, we have to use a composite section to model the concrete topping to increase the stiffness of the girder, and also we have to use the dummy transverse beams to model to make the girders work together. So we are, by this model, we are satisfying the role of the deck, which is one, making the connection between the girders to make them one system and then work together. Another one is increasing the stiffness of the I-Girder itself by making it composite. So that would be a very good method for the global analysis. Using the beam element is pretty fast. The modeling is pretty fast. It's pretty easy. You need less considerations, and then the analysis is done pretty fast. But it has some limitation as well. For example, you may not be able to see the warping stresses or warping deformations. You can study the buckling, like a global buckling, but if it comes to the local buckling or web buckling, so you may need to use a plate element. So these are the limitation and advantage of each elements I talked about. And now we see when we have a composite section, the I-Girder with the concrete topping, how can I model that? What I have here for you is a hybrid method, or just using a combination of these two, using a beam and plate element at the same time for different purposes. Here I got only two models for you. In the modeling top, I use plate element for the web, and I use beam element for the flanges. The reason I did that is that in this model I can study the buckling of the web, which is pretty important for me, and I wanna understand. I may see the buckling mode shapes and all those. In the other model, like the one in the bottom, I modeled the entire beam with the entire girder with the beam element, and then covered it with the plate element to represent the concrete deck. So the reason I did that is that it makes my analysis pretty fast. I can just simply model the girder with the beam element, and then cover it with the plate element and run the analysis quickly, get the result. And then the third method was just using a composite section. As you can see here, everything, the girder and the concrete, are modeled as single element, which is a beam element. As you can see here, this is only one beam element which carries the sectional properties of the girder itself and then the concrete as a composite unit. So you can see these examples. So in this model in top, I used plate element for everything. So the webs, flanges, concrete deck, this diaphragm, all of them are modeled by using the plate element. So this is a very accurate model, very sophisticated model, and I can study it pretty well. I can understand a lot of like effects that I have. But this one takes a little bit more time compared to the beam element. For example, if this one, which is the composite section, takes let's say 20 seconds to complete the analysis, the other one for the plate element may take about 2 minutes or 3 minutes to finish the analysis. So a little bit more time required for this one. But here I can see a lot of like more effect. Here I can see like a global effects, like I can understand the failure mode shapes of the buckling. I can understand the bending moments and then shear forces inside these each element, and the analysis is done pretty quickly in this model. Okay, so this is a model that you see is like a complete steel curved bridge, and you can also model the pier, cab, and pier. So next session, please join us, and I will show you how you can create all these elements, how to create the girders, the cross frames, the pier cabs, and also the concrete deck. All right. So the third part, I want to talk more about the analysis and then the consideration for the construction. So staging of steel erection is considered in addition to the sequential placement of the deck. The deck is considered to be placed in the following sequences for the constructability limit state. For example, you see here, they are not, you know, we are not pouring the concrete all at the same time or like in order from left to right. So you see that this is the first sequence of pouring concrete, then the second one, the third one, 4 comes here, and then finally the 5. So these are pretty important to follow these methods in case that we are not in a trouble during the construction. So for the constructability limit state check, the non-composite steel is checked for the moment resulting from the deck placement sequences, or the moment computed assuming the entire deck is cast and at one time. Which one is, I mean, whenever, either one which is larger, so we're going to consider that one. Okay. So here I showed you some of the erection sequences. So that's pretty important. They are not talk about this a lot, and showed some statistics, and then came up with some result that how this gonna affect, and then how we can we need to develop a code for these construction sequences. Here I just showed you some of the, just a general overview. I'm not going into details. They are not completely covered everything. I just show you how we can do that. For example, if we have this bridge completed here, so we could have in the first stage, we could have only this girder in the right side with the abutment and then the pier. In the second part, we gotta have the rest of the girders, and start pouring the concrete on the left side, on the right side, then pouring the concrete on the left side, and finally pouring concrete in the middle and complete the bridge. So in these sequences, it's important to find out what is the vertical displacement, what is the bending moment that each element experiences, because these will be all important for the construction. Otherwise, you may come up with like a misplacing of some element which is deformed based on the self-weight. All right, so in this example, in this slide, I show you how the construction is done. So let me just show you in the different angles also. Okay, so it will be like a construction at 3 parts. So here we model the girder itself, we model the cross frames, and also the composite deck with the concrete itself. So apart from the construction stage analysis, which is pretty important and critical, you may have some like an integral bridge. So integral bridge means when your girder is integral with your abutment or with your pier. So in this case, probably some type of load like a temperature load come into equation and plays an important role. So you have to consider those. Or if you want to study the soil structure interaction, so definitely because behind this soil, behind this abutment, you have the soil. So you have to somehow see those effects. And you have some piles, and then again you have this soil structure interaction. So you can simply, you have to be able to model those with the corresponding springs or seeing the effect of temperature. So let me just quickly show you some of the temperature loading which need to be done. So we have actually three type of temperature effect. One with the uniform temperature changes, so entire the structure heat up at the same time with the same temperature. So we can simply apply those temperature to entire the structure. Doesn't matter it's girder or the slab. Another one is the temperature gradient. So the temperature gradient means that for example, the top part of the section may experience more heat compared to the middle part. For example, because here we have shadow and then it's not there's no sun here, so this part may not experience any high temperature. So you have to be able to apply these nonlinear temperature gradient. And next session, I'll show you how Midas Civil can handle this. Another one will be temperature effect during the construction stage. So that's also pretty important because if they depends on the site that you have and the size of element that you have, this temperature might affect the construction. So you have to be careful. Another analysis which is important for steel curved bridges is the moving load. So the moving load could be pretty critical somehow. For example, we could have this. We have the centrifugal forces which need to be considered, and definitely you have to calculate it correctly and see the effect, because otherwise it might cause some damages to the the vehicles, or we have some accidents. Anyway, along with that, it's important to understand which element on the structure under the moving load or the combination of moving load and the dead load experience the maximum, let's say, bending moment or maximum shear forces. Then we can design our structure based on that critical element. So in Midas Civil, you have unique tools like a moving load tracer, as you can see here. For example, if certain element, let's say this one, experiences the maximum bending moment, or the one interior one, so you can find out that what load pattern or where is the location of the truck which causes such an effect and causes that much of a bending moment on that element. Then you can save it as a static load, which I can discuss them more in detail in the next session, in the training session. Okay, so we talked also about the centrifugal forces as well. Another important case for the steel girders are buckling analysis. So the buckling is actually could be a failure point for the structure, so it can cause the failure to the entire structure. So we have different type of buckling. I talk about them, and that's pretty critical to study this. Just take a look at this model before we go ahead and talk about the different type of buckling. As you can see here, we are seeing the local buckling, or the the web buckling here. Also, we can see some distortional effects here in the section. So all these should be studied. And if you model for example, in the top model, if you model the bridge with the beam element, you will not be able to see these effect or buckling of the webs. You can still see only the global buckling, or based on that equation, the Euler equation. So let's talk about the different types of buckling. You have lateral torsional buckling, which as you can see, the section can go out of plane, and then you see what happens. We have additional rotations and also displacement. We have lateral distorsional buckling, which not only displays but also we have distorted web, and definitely causes the flange also rotate. And also we have local buckling. So the local buckling technically could be the web buckling or the flange buckling. So this is why in that model I modeled the web part with the plate element. Then I can understand or can see these local bucklings if going to happen, and then model the flanges with the beam element, because there is less possibility that buckling occurs in those areas, because we have the relatively longer or deeper webs in the I-Girders. And then another analysis case would be extreme events. As I said, the extreme events could be earthquake or the floods normally, but here I'm just talking about the earthquake. If in your region is a if in your area you need to do the seismic analysis, so definitely you need to model the soil structure interaction. Definitely you have to be able to model those piles and model those nonlinear springs or nonlinear boundaries in your model to be able to get the correct response of a structure based on the earthquake that you get from those. So next session I'll show you how Midas Civil handles that, how we have the predefined functions, well-known functions like a kinematic hardening, and also Takeda models, and also we have user-defined, which you can copy-paste your data from Excel, and then you come up with like a correct, complete nonlinear curves of the these springs, and then how to apply these ground excitation to the structure. All right, the same thing for the abutment. So when you have abutment, you can simply apply these springs, and so it's gonna be a system of the springs and then the dashpots. And another method which you can see here is, you see here we modeled entirely pile system with the pile cap and everything. Here we removed that pile group and then replace it with a single spring. So we call this as a general springs. This is a option available in Midas Civil, where you can just remove the entire pile group and apply a general springs which represent those pile group, and then represent the soil structure interaction of those piles with the surrounding soil. And how we define that, we are using a 6x6 matrices of mass, damping, and stiffness. I have another session which I discuss about them, so you can go on our website, www.goodengineers.com, and have access to those nonlinear analysis type of things. All right, so in the last part we talk about the design consideration. I just quickly pinpoint these, and I'm not going to go in that much of detail. So the span arrangement is pretty important, and the engineer should be aware of that, to come up with like kind of balanced type of structure. So rule of thumb says that for example, if you have like a 3 spans, so the end span approximately has like a 80% of length of the center span. So in this way we are coming up with kind of balanced structure, and so we are not coming up with one span had like a very large section and other spans having small sections. So that's pretty important to arrange those spans. Also the same thing for the girder spacing. Girder spacing are pretty important as well. And then the detailing about the those framings and how to connect these girders, and some other considerations like the maximum section twist, which some codes are the values you are seeing here. I got them from Pennsylvania DOT, but each DOT may have their own consideration for this. So for example, for section twist, it should be smaller than 1/8 of the feet or the feet. And then for the total differential deflection, so we're gonna come up with like a it should be less than S over 100, which S is the spacing between these two girders. And finally, the constructability is important. You have to take care of this in your design consideration. Okay, that's all I want to show you today. I hope you guys like the session, and if you have any questions, please feel free to send them over to me, and I'll be so happy to answer your questions. Thank you so much for your time, and you have a great evening.